all of you once again, and basically, I would like to go back to the environment that Professor Shajul Das had created a few minutes ago. So it's more like an adda rather than ALAP, if you say so. The track was distributed computing, so nowadays distributed computing is everywhere. Okay, right? Certain distributed things are all over the globe, certain distributed things are there in a chip, right? And so I'll start with the name of a book, Laws of Thought. And that book was published in 1854. Okay? Any idea what could be the subject matter of this book? It talks about laws of thought. This was a book authored by a British mathematician, George Boole. And it is in this book that he had given all of the Boolean algebra that we use today. Right? So this is the book on Boolean algebra. And this was in 1854, and in 1947 we have the breakthrough in electronics in the sense that transistor was invented. So it was almost 93 years, okay? And then the transistor was used as a switch first in 1953. So you can see that almost after 100 years, the Boolean algebra was put into practice in the sense that when you are designing the computers, that Boolean algebra came very handy. So the computer design, program design, all of that, right up to today, is based on Boolean algebra. And there is a relentless development after that, and the law that governs this, or governed this rather, is that the number of transistors in an IC doubles approximately every 2 years. This was the famous Moore's law. Gordon Moore, who later became the one of the persons who started Intel Corporation. So this Gordon Moore in 1965 specified this law, which is known as Moore's law. And if you start from 1971, which was the birth of the first microprocessor by Intel 4004, and for the next 5 decades, this law was active. Now, of course, people are talking about quantum computers and all that, but even now, this is still in existence. Let us see this. Over this, it's too small to see, but here you can see the 1971, when 4004 was there, and it had a total number of 2,300 transistors in it. You go to the other end, which is 2011, and you can see the number of transistors have gone to that. This stops at 2011, but if you see the figures in 2017, okay, you'd see that it really has gone from minuscule to enormity. This is the 2,300 transistors, and the size of the transistors were 10,000 nanometer. If you come to 2017, this AMD 32 core EPYC, it has got 19.2 billion transistors. Okay, and it's 10 nanometer, the size of the transistor, so you cannot see that even with the microscope because it's lesser than the wavelength of light. So this, if you calculate that, you would actually find that in these 46 years or so, it really is almost 2 to the power of 23. So that's the kind of vision that Moore's law had given. Well, if you compare that with the kind of machines that we had in the first generation, ENIAC, the smartphones that we have in our pocket is about 100,000 times more powerful than the early computers, and those early computers occupied 1,800 square feet, so it's a big, nice, flat thing, and weighed about 30 tons. So you can easily compare the kind of machines that we have in our hand these days. So as computers grew in computing power, both the power of computation as well as the storage space. The magnitude of problem that we wanted to solve with these machines also were correspondingly higher. And then we were not even satisfied with that. We combined large number of such powerful machines to give rise to parallel computing and distributed computing, which was the track that we just finished. And we are now in the realm of very large database, data mining, big data, and all those things. But if you turn your eyes from those number crunching things to the currently renovated artificial intelligence, you'd really be seeing that the concept of AI, just like that Boolean algebra, was first made in 1956, and the AI was continuing all these years, but the sudden, advancement in computer technology made it with different types of algorithms, and these algorithms have made machines which have self-learning abilities. Okay, so we now are in the area of artificial intelligence with machine learning and also deep learning. So where is this basically taking us to? That is what I am trying to show you. Artificial neural network, we all know it has got input layer, output layer, and number of hidden layers in between. But the complexity of these ANNs have become tremendously large these days. Okay, and you see, this is the kind of thing. The deep learning involves ANN consisting of all these layers, and over time, an algorithm which is called backpropagation, it basically tweaked the connections between the different units of the hidden layers. The given input tends to produce the corresponding output, and it has given tremendous results. You've got all these things that are there, but I'll take you to one example in Mount Sinai Hospital in New York. They had created a deep patient, which is actually a deep learning machine, and it was trained with data from 700,000 patients. As a result of that, the machine was able to discover a wide range of hidden ailments way better than expert doctors. But the problem actually started after that. The deep learning ANNs remain something like a black box, because you see that self-learning algorithm is such that it is learning just like the human beings do. Okay, we're trying to make those neurons just like the neurons in our brain. So what happened is that it had used that to tweak those interconnections, those weightages that connect from one hidden layer to another hidden layer, and that black box is something now that cannot be readily understood. Okay, so the doctors say that if only we could build these models, but we don't know how they work. Okay, so we have now created machines and algorithms by which the machine is learning by itself, and when it is generating the result, it is better than what we can do as human beings in that particular domain. I am not saying that we are surpassing the human intelligence, but in that particular domain it really becomes an expert. Okay, and why is it different? Take for example the self-driving car of the chip manufacturer NVIDIA. This is unlike the one that have been created by Google or Tesla and so on. In this particular machine, not a single instruction was provided by an engineer or programmer. So how did it work? The algorithm that had taught itself to drive by watching a human do it. So it is watching the way a human driver would be reacting to situations. It's learning from there, and then it is taking over the control. So this is unsettling, because the experts say that suppose tomorrow one of these self-driving cars stop at a green light and does not move. Then if we want to debug that, we have no way to do that because we do not know how that learning had taken place. Okay? So, basically what is happening is that all those sensor data is going over the huge network of artificial neurons, and that output of the ANN is giving the command to operate the accelerator, steering and brakes and etc. So, even engineers who built it cannot isolate the reason for any single action, and it cannot answer the question why it did what it did. So this is an open question now. We have never ever built before this time machines that operate in ways their creators do not understand. Okay, so this perhaps have actually prompted Stephen Hawking to say that we must, at this point of time, apply artificial intelligence with a lot of caution. So this is a presentation of a very different nature. I just wanted to bring your attention to the fact that what these large machines and high power machines are going to do, and how the algorithm, which is the subject matter of this conference, is taking a turn, and how exactly that will work, we really do not know, but as researchers, we must keep our eyes open to those problems. Thank you so much.
Thank you, sir, for such an enlightening talk. Now I'll request Professor B.N. Chatterjee to felicitate Professor Dash with a small token of appreciation from our side.